The specific heat capacity of a substance is defined as the energy, which is measured in joules, that's required to raise 1 gram of that substance by 1 degree Celsius. So for example, and the specific heat capacity is notated with a lowercase c, the specific heat capacity of water is 4.184 joules per gram degree Celsius. If we think about this unit for a minute, that means it's going to take an input of 4.184 joules in order to increase 1 gram of water by 1 degree Celsius. So that kind of explains why there are funky units for specific heat capacity, but specific heat capacity is most frequently measured in joules per gram degree Celsius. Now, you'll notice the specific heat capacity for water being 4.184, whereas the specific heat capacity of something like aluminum is 0.90. What this means is that water is more able to absorb heat without as rapidly changing temperatures. If you think about putting a sample of a metal, like aluminum, into a fire, even for a brief moment, that's a lot of energy being subjected to it. And since it has a low specific heat capacity, it can only absorb 0.90 joules per gram before it starts changing by a degree Celsius. Whereas if you took an equally sized sample of water and you put it into a fire briefly, the temperature change of that water would not be nearly as dramatic because it takes 4.184 joules in order to change 1 gram by a degree Celsius, whereas it takes far less to change a metal like aluminum. So this specific heat capacity is very useful in this equation here, where Q equals mc delta T. And what this is, Q is the heat or the energy being put in or taken from a substance. And again, that's measured in joules. M is the mass of the substance, measured in grams. We just defined C as the specific heat capacity. And we said that that's measured in joules per gram degree Celsius. And then this delta T, as you know, delta means change, so this is the change in temperature, which in this case would be measured with degrees Celsius. If you think about these units and you line them up in this equation, first you'll have joules equals grams times the specific heat capacity is units of joules per gram degree Celsius times the temperature change, which is measured in degrees Celsius. You can see on this right side that this gram will cancel out this gram on the bottom of the fraction, and this degree Celsius will cancel this degree Celsius, leaving you with the true statement of joule equaling joule. So therefore, we know that these units are logical. Now this equation is useful because if you know 3 of these 4 variables, you can always calculate the other one. For example, we have 15,500 joules of heat being applied to a 50-gram sample of water. If that water is initially at 25 degrees Celsius, what will be the final temperature? So if we think about our equation, Q equals mc delta T. Q again is the energy, which is 15,500 joules. So 15,500 joules equals, the M is just your mass, and this is a 50-gram sample of water, times C, which is the specific heat capacity of water. You don't have to memorize this, but you will because you'll have seen it so many times. But the specific heat capacity of water, as we said, is 4.184 joules per gram degree Celsius. So the specific heat capacity of water is 4.184 joules per gram degree Celsius, which leaves us with our delta T, our change in temperature. Now you have to be careful because this is the change in temperature. This 25 degrees Celsius is the initial temperature. What we're calculating down here is merely the change in temperature. Since we're applying heat to this, it's going to represent an increase in the temperature. So whatever this value is for delta T, we will have to add to our initial temperature. For example, if the change in temperature was 5 degrees, 25 plus 5, our final temperature will now be 30 degrees. So all you have to do is plug this into a calculator. And when you plug it into a calculator, you find your delta T is going to equal to, it looks like, we have 3 sig figs, 74.1 degrees Celsius. Now you have to be careful here. This is not your final temperature. This is merely the temperature change. You were initially at 25 degrees. Now you've increased it by 74.1. And because we're adding, we don't look at sig figs, we look at decimal places. The best answer you can provide here would be 99 degrees Celsius. So what you would have done is, by applying 15,500 joules to this 50-gram sample of water, you would have raised its temperature from 25 degrees to 99 degrees Celsius. So it's just about to boil. So another concept that we need to define is system versus surroundings. The system is whatever you're focusing on in that given situation. In this previous example right here, we were applying heat to the water, so the water would be our system. The surroundings is everything else in the entire universe. It's almost irrelevant to think about it too specifically, because in our previous problem, we were focusing on the temperature change of the water. We knew that 15,500 joules of energy was being added to the water, but we did not necessarily care where it came from. So we can say that it simply came from the surroundings. With that being said, the heat or the energy Q of the system has to equal the negative Q of the surroundings. Because if energy is going into the system, then that energy had to come from the surroundings. Or if the system is what is losing the energy, that energy has to go into the surroundings. So negative Q for the system, a loss of heat for the system, would mean a positive Q for the surroundings, or an increase in heat for the surroundings. So now we need to define these a little bit further. In this top situation here, the Q for the surroundings is negative, meaning the surroundings are losing energy, meaning the system is gaining energy. In this situation, with the system gaining energy, that's defined as an endothermic process. If your area of focus or the system is an endothermic process, if your system is gaining the energy, that is an endothermic process. Down here, the system is losing energy to the surroundings. So again, as the system loses energy, we've defined that as an exothermic process. So if you were to consider, I'll draw a lovely ice cube. This ice cube, and I just set it on a table, and it's at room temperature. Let's say it's 25 degrees Celsius in here. What's going to happen to this ice cube? Well, it's sitting out in the warmer room. That ice cube is going to begin to melt. I want you to think about the energy transfer here. If the system is the ice or the water, because they're the same thing, if the system is the ice, energy from the system or from the surroundings will be entering that system, because energy always travels from hot to cold. So as this ice begins absorbing that energy from the surroundings, it will melt into water. Since the system gained energy, that is an endothermic process. The melting of this ice would be an endothermic process.